Uh, Okay. Uh, Hi everyone. I'm Tan. Today I'm presenting our work, moment matching reinforcement learning, a joint work with my collaborators Sunil and Sveta. So let's get started. Deep reinforcement learning has surpassed human level of performance in several important domains. For example, AlphaGo is the first computer program that uh, defeat the Go professional world champion. But there are still many fundamental and practical challenges in reinforcement learning. So here are some of the challenges. So sample efficiency. So in reinforcement learning, it's known that it requires a lot of samples to learn useful policy. And in real world reinforcement learning, usually we learn from block data because the interaction with the environment is very expensive. Some other fundamental problem like convergence, stability, and robustness in reinforcement learning is also important. And generalization across different tasks, where we train the agent in one task and require to generalize well to the unseen task. It's also the active research domains. On the theoretical side, so people derive some generalization values in reinforcement learning, such as visit dimension, covering number, elude dimension. And also, another part is robust and informative presentation learning for reinforcement learning, where we try to learn a good presentation. And this is also the focus of this work. And so the motivation is that it's based on the high-level motivation from self-supervised learning principle. So to encode an object, we set up a learning task between different parts of an object. For example, given a sentence context around the world, the goal is to learn to predict the missing word, like in the skip gram and BERT model in NLP. Or in computer vision, we can rotate an image and predict the rotation angle. And we can model the input view or by data augmentation and make the learning invariant to this change. So self-supervised learning for is now for high-level physics objects such as images, videos, text, videos with sound. But here we take the inspiration from self-supervised learning for low-level mathematical objects, which are probability measures. We predict different parts of probability measures for the Bellman dynamic. The standard RL, so we predict the mean of the return distributions, but here we predict the moments of all orders of the return distribution. So by trying to predict different parts of the return distributions, you end up learning the intrinsic properties of return distribution, and you can, at the results, improve the presentation. So here the intrinsic properties are the intrinsic randomness of the environment and the policies itself. I will briefly talk background reinforcement learning, distribution reinforcement learning, our ideas on moment matching reinforcement learning is beyond the moment discussion. So reinforcement learning is a learning paradigm that's uh, learn via interaction with environment. So with the goal is to maximize the total rewards. And for example, some practical real world examples are like learning to drive cars without collisions or learning to play games. So here the formal setting. We have the agent interacting with environment model by the Markov decision process MLP, which specified by state space S, action space A, reward R, transition kernel, which P, which specify next state given current action and current state, and the discounted factor gamma. So a policy pi maps a state probability of actions. And the sum of future rewards following a policy pi is a random variable computed as follow this one. So this is a total reward follow the policy pi in given the current action and current say action A. So in Q-learning, the standard reinforcement learning, we maximize the action value function QR, Q pi of action A, which is expectation of the return distribution. And in practice, we can parameterize this action value function by deep neural network. to improve the generalization to insane states, such as the famous DQN. So in other words, Q-learning learns the first order moments of the return distribution. So a natural question is, can we learn all the statistical properties based on beyond the first order moments of return distribution? And here, though the goal is to learn to maximize the first order moments of the return distribution, we can make the neural representation capture the intrinsic properties of return distribution by learning all the statistic aspects of return distribution as well. So in this work, we will show how to learn the moments of all orders of the return distribution and how it leads to significant improvement in the artery games. Since a fundamental thing here in this paradigm is the distributional Bellman operator. So it specifies the relation between different return distribution across, say, action pairs along the Bellman dynamics. So the equation are like this. To make it easier to understand, so if you take the expectation both sides of this equation, so it's something like this. So it's will reduce to the standard reinforcement learning. So it's, in other words, the equation here take into account the intrinsic randomness of the environment and the policy. And the goal here is to learn the set return distribution satisfy the distributional Bellman dynamic. The challenge is that it's a sample-based problem. We need to learn the set return distribution through the interaction with environment. So it requires efficient estimation of the return distribution using certain empirical samples. And also the space of probability measures are infinite dimensional. So we require some parameterization such as deep neural network. Our approach is that we model a set of determinate particles of return distribution via maximum mean discrepancy. And the determinate particles are parameterized by the neural networks. Maximum discrepancy is the maximum between two expectations with respect to distribution over some function space. And if the function space here taken to be the unique bar in the reproducing kernel Hilbert space, so the empty distance has closed form like this. So it's just the distance between two mean embeddings of two distribution. And in practice, we can approximate this distance by the empirical sample of the underlying distribution. And this the empties can also be expressed in terms of mean difference in the feature space. And in the case of the Gaussian kernel here, so the high dimensional feature map phi s can cover the moments of all orders. So minimizing MMT becomes matching moments of all orders between two distributions. This concrete our concrete algorithm is we represent a set of determinate particle by neural networks, and then we given a sample transition current state S, current action A, reward R, next state S prime, next action A star. So and it's the determinate particles. We will compute the target distribution via the distributional domain operator like this. So it's simply scale the particle by gamma and then shift by reward R. And plugging into the empty distance, so it's become like this. So this one have two forces driving the equations here. The first one is the repulsion forces, which keep the particle away from each other. So it's prevent the particle from collapsing into a single mole. And the second term, the attractive force, we pull this particle closer to its target particle. So these two forces are automatically balanced during the training. Okay. So we present some results. So the benchmark here is the Atari benchmark. And the baseline of the famous DQN learning, and then the QRDQN. So QRDQN is also a distributional RL, which predict the quantile return distribution. But here in our framework, we predict deterministic particles of the return distributions, and it doesn't require statistical order. So you can see it's our framework, our form in this game. And and what about the result for all games? So in all games, our framework provides significant empirical improvement over the existing distribution RL agents. So here's some demo. So in the left, okay, so this the first column here is the three consecutive frames in the breakout game played by our algorithm, and this is the the return distributions approximated by our algorithm. So at the balls moving from left to the right, uh, the left action less beneficial. So that's why our algorithm plays the probability mass of the left action to smaller values. It means that our algorithm can distinguish a beneficial action with less beneficial actions. So you can see all the demos on other games following these YouTube links. So discussion, we have proposed a novel framework to learn to perform moment matching in reinforcement learning, and our framework is simple yet highly flexible in modeling statistical efficiency and scalability. And we achieve a significant improvement in on-the benchmark. More details you can see in our reprint. Thank you.